Thanks, Chris. And thanks for giving me this opportunity to talk here about my work. So this work was done a couple of years back when I was in the Tata Institute in Mumbai as a postdoc. Now I'm a postdoc in IFIC Valencia. So this is, by now we are all experts on dark matter capture. And we're like, this is a schematic diagram. So a dark matter particle coming from like infinity with the halo dark matter, the velocity is u. And as it enters some celestial object, okay, it may be anything, white dwarf, neutron stars. This velocity is w, and w squared is u squared plus the escape velocity of the object square. And as it enters, it can scatter once, and its velocity after the first scattering can come down the escape velocity, and then we say that it is captured after the first scattering, or it may do multiple scatterings inside, and its velocity after n number of scatterings can come down or come below the escape velocity, and then it is captured in this bound orbit. So the number of scatterings is typically given by comparing the dimension of the star, which is like r, and the free streaming length. And if we do n is the number density, this is sigma over r squared. So more compact the objects are, we expect more number of scatterings are required to bring it down to the escape velocity. Also, it should depend on the mass of the dark matter, because heavier dark matter means that loss of energy per scattering is small, and so it will require many number of scatterings to come below. So a quick recap of capture via single scattering. So this is done by Gould and many other people earlier. So this is the capture rate, and this is the total number of targets and the number density of dark matter. So the fractional loss in energy is a very simple calculation, lies between 0 and beta, where beta is this factor. And for capture, we need W to be greater than the escape velocity. Otherwise, it will not enter the celestial object. This is this W. And this is, so now it's a very simple way. So we just divide for the probability of capture, we divide the allowed region divided by total region, which is beta. And just by dividing the allowed region by the net amount of the region or the net length of the region, we are assuming a sort of uniform distribution, and this will be the next part of my, or in the later part of my talk, I'll say that this is not always true. So, but now we consider this simple like uniform probability distribution for the fractional energy loss. So this is multiple scatterings. This was first done very systematically by Joe Bramante there and his colleagues. So this is the capture rate at the nth collision. So this is dependent on the size of the object, the probability that there will be n collisions in the first place, the dark matter flux, of course, and the probability that after n collisions, the final velocity is less than the escape velocity of the celestial object. So the probability, this P can be done or can be like modeled via Poinsot. And this is the optical depth, which is just the net cross section over the net geometrical cross section of the star. This is just a definition. This is so do this, and we see that for P1 we recover C1, and which is a good check. And like this was also first done in the Bramante's paper, and we did some modest improvements over some of his results and conclusions. So delta E is given by Z. Z is this cos square of theta recoil, and the capture probability now is given by, I'll hurry up, so given by this integral. So this integral can be done exactly analytically without any thing on the Z, but in the Bramante's paper, they replaced each Z by their average value, which is half, and so they have this G, and this G by construct lies between 0 and 1. But for us, we have to be careful and check that what are the limits, and we get a minimum U and a maximum U. This is understandable physically, because beyond the maximum you would not capture at the nth collision, and beyond the minimum you are already captured at the n-1 collision. So these are like physically viable. So now the total capture rate, the thing is how much this summation should run. So this summation, we said that, okay, since this is the capture rate and like multiplying it by the lifetime, we These are the numbers. This should be an integer. It cannot be less than 1. And we truncate the series when it becomes less than 1. This is just like a convergence test, but in a more refined manner. So we see that for very compact star and very high mass dark matter, neutron star, so the maximum allowed number of scatters that can happen is like 20 or 25, which is not that big. So we, like using these things, we try to give some bounds on using white dwarfs in the M4 globular cluster. These are the data points, and we said that the dark matter luminosity cannot be higher than the observed luminosity, and these are the bounds. I'll quicken. So this is part B, where we introduce effect of light mediators, and in the first slide I showed that this assumes a uniform distribution. So the distribution of theta cm, in which is the distribution of the scattering angle in the center of mass frame, is given by this. And the recoil, this z thing that I showed you earlier, is like related to this theta cm via this. And knowing this, we can now find a distribution of delta E by E, given the fact that we assume some d sigma d omega. So we say that, okay, let's take some generic equivalent potential in the relativistic, non-relativistic bond regime, which looks like this. So this is our distribution of Z, which we call SZ. And here we only concentrate on capture via single scattering. And the initial capture rate, we didn't have any factor of SZ. And now we modify the uniformity of the capture rate via single scattering, or probability of capture via single scattering using SZ. We find this. And in the M5 tending to infinity limit, we see that we recover everything that Gould has. So this is the capture rate. This is the geometric cross-section for a neutron star. Okay. And we try to like derive some bounds in the way that we did for white dwarfs. When sigma is the maximum, which is the geometric cross-section, we tried to calculate the dark heating with a T like 1000 Kelvin neutron star for different masses of this mediator. And we see that for very light mediators, we cannot like provide some bounds from this heating perspective. So these are the take-home messages, that we did some improvements over the previous work on multi-scatter dark matter capture, and we gave some bounds. Okay, of course, this bound depends on the density of dark matter in globular cluster, which is now a matter of debate because it's very high. Some people say very high, very low, so that's it. And otherwise, in part B, we generalized this dark matter capture in case of arbitrary mediator mass. And if it's very light, this heating is washed out. That's it. Thank you.
I'll leave you the microphone.
Thanks, really, very nice talk. Could you just go over what's going on with the heating being washed out at the end? Okay. I just don't know the details.
So, I had to mention this. So yeah. So this is for a given constant cross section, right? So if we look at this, so this means that the integral of this equation is, we fix it to a certain value, which is the geometric cross section, and then try to see that what is m times capture rate, and compare with this observation. Observation is we know the temperature, we know it's via the Stefan-Boltzmann law. And like, so I think this is a confusing plot, because people think that this alpha and this mu is the reduced mass, which has the dark matter mass also, m phi. So along each of these curve, none of dark matter mass or the alpha is constant. They are varying together, so that the net cross section is constant. I think that was your confusion you were getting, right? Because you are trying to scale everything and see that why this 0.25 why this 0.25 washes out. But yeah, I mean, this is a bit counterintuitive because the net cross section is fixed and all the parameters are varying among themselves to make it go.
So as the as the mass of the dark
Yeah,
matter
yeah,
goes
so,
down, it becomes more pronounced in effect as you decrease the mediator mass. Okay, thanks.
How much would you say?
I can hear you.
How much would you say your modifications to the accumulation rate versus previous change the estimates in the end?
In this scenario?
Sure, yeah.
Yeah, so, I mean, that would depend, of course, on the mass of the mediator. And, I mean, it can be substantial, right? Because if you see that this is the usual thing that people do, because this is the M phi tending to infinity limit, and if you change, I mean, you can vary the heating, which means you can vary the capture rate by a lot. But it's slightly model dependent because we have to have some sort of this structure of the differential cross section.
Any other question? Yeah.
Hi, hello. I have one question regarding your summary. Can you just go to the last slide? Yeah, like the limits that you have reported, recently I have saw the paper by Bell where they have used some improved method to obtain the limits from the white dwarf, and they have, I think if I remember correctly, they have compared the limits, their limits with your paper. So do you want to say anything about that? Yeah, the Nicolay paper where they say that, okay, I can discuss that later, where they use Yes, yeah. Just you just say that the most stringent limit that you were saying you got from the globular cluster, where they have also did the same study and say that it is kind of like one order, few order worsening that the limits that you got. Yeah. Mm-hmm. Okay. That is what I wanted. Okay. Thank you.
Any other question? Okay, so let's thank our speaker.